whoops, forgot to include this page in the part before on activation energies. So this is a companion problem, and we will leave it as such, and I will post the answer for the companion problems for this. Activation energy plotting problem. So we went over the linear relationship for the Arrhenius equation, and the Arrhenius equation K equals Arrhenius pre-exponential factor minus e to the minus EA over RT. And when we did that, we decided that a plot of the natural logarithm of the rate constant versus 1 over temperature in units of 1 over Kelvin would be a linear plot with the slope being related to the activation energy. So what you need to do to solve this problem is take your rate constant, take the natural logarithm. I would hope that you could do it in Excel or some other spreadsheet program using the equals ln function within Excel. Here, you're going to take your temperature, you're going to do equals 1 over temperature, 1 over each of these numbers. And then you're going to plot it. You're going to add a trend line. And I always like to add r squared, the correlation coefficient. But what you need is you need to add a trend line and display the equation to get that slope. And then tell me what the activation energy is. To solve this problem. Now, catalysts. We're only going to say a little bit about catalysts, and but it is useful to know this, especially moving forward in our study of chemistry. A catalyst generally uses an alternate lower activation energy pathway between the reactants and products. Occasionally, the catalyst increases the number of effective collisions, increasing the Arrhenius pre-exponential factor, but typically how we think about it is that catalysts decrease or lower the activation energy. So here's some reaction energy diagrams without a catalyst. Let's say we have an exothermic, and I'm going to mention the mechanisms here, and we can say more about this if you'd like, just let me know. So reaction energy diagram is going to say potential energy on the y-axis, reaction progress. Well, that's good, yeah. And for exothermic, remember, you've got your reactants. At a higher position, you've got your products. At a lower position, and the difference in potential energy of your reactants and products is your delta H of reaction, the heat energy given off. And what we said was that if between here there's an activation energy, I'm going to draw it kind of high, but there's a reason. And our activation energy was from the reactants to the top of the energy hump. And we just barely mentioned so far that this is the transition state, but there is something that exists there, and that's our activation energy. And this is considered a one-step mechanism because there's one hump. Now, what we can do is for a catalyst, and let me see if I can add a catalyst here. There we go. When we add a catalyst, we're going to lower the activation energy. And two things can happen. One, you can lower the activation energy and still have a one-step mechanism. You can also lower the activation energy and have a two-step mechanism. And actually, let me take a minute here to finish the picture over here. Then I'll come back and add the catalyst part. As we know, we can do the same thing for an endothermic reaction. Doesn't matter where they are. Let's put them here. Reactants are always on the left. Products are always on the right, and that's what reaction progress means. It's progressing from reactants to products. And then here, we also have our delta H. And I typically call this delta H reaction, so I should type that in. And then for an endothermic reaction with a two-step reaction mechanism, we would actually draw two humps. That's what our picture of a two-step reaction mechanism is. And these are without the catalyst. And activation energy. These pens is the one I need to use. There we go. Is going to be from reactants all the way up to the top of the highest hump. And so, or to the top of this hump here. And now, let me see. There we go. So now the next slide says reaction energy diagrams with the catalyst. The catalyst can have the same or a different number of steps in the new lower energy pathway. So I'm going to draw them actually back on this page instead of on the next page. And here we go, reactants and products. Let's suppose that the catalyst has a lower energy two-step mechanism, or a lower activation energy two-step mechanism. What that would look like for an exothermic reaction would be two humps, lower in energy, and the activation energy is now always to the first hump. And then, so here is our new activation energy with catalyst. And then over here, so it's a two-step reaction mechanism. It doesn't happen often, but you can imagine that over here, that there's it goes to, so catalyst with lower EA and a one-step mechanism. And that would look like this. Comes up, lower energy, one hump, goes straight to products. And our activation energy here catalyst is always from reactants to the hump there. And it gets more complicated because the second hump could be higher, but we won't talk about that. What's important for us to know is that catalysts lower the activation energy by changing how the reaction occurs. That change and the lower activation energy allows the reaction to go faster because, as we've seen, lower activation energies allow or lower the energy for the reaction to occur.